Yes. Hello, Spencer. Hello, Connor. We'll start in a second. Well, it was an exaggeration from me. Okay. Yes. Okay. So we are basically doing the homework now, right? And if you have the code, you can try doing it yourself and finish it. It's possible to finish in 10 minutes. I will be here for 4 hours if needed, but it is, what to say, an exaggeration of resources. So before we go forward, I am going to remind something. So this is, I'm not good in math, it's arithmetic, so either 25th or 20, probably lecture 25. Once you are trying to find the eigenstate of the harmonic oscillator, right? Not yet in the discrete space of eigenstates, but just in a regular way, as a continuous function of variables, right? And we found that it is a Gaussian shape centered at the equilibrium position. And by solving differential equation, we found that in the denominator of the power of the sparse quarter, and in the denominator, it should be not. Here in this form. So the width is linearly proportional to the constant and inversely proportional to the mass frequency. I'm going to just fill the space. If you know how to do not wait for me. I will not do some boring stuff.
Oh no, we're listening.
Huh?
We're listening, don't we?
You do not need to explore. You can. I appreciate it, but if the goal is to complete homework, it can be done without listening. So I'm going to make a comment to connect the stuff on the board from previous lectures and the assignment of homework that we do. And again, if you are in a rush, just download the code and write it again and again with different values of X bar parameter, and would record the images and the observations. But I'll try to store. So X bar parameter at the beginning of the code is literally this signal. So we suggest assignment is to consider different initial values of this signal, which is abbreviated as X bar. So variance in the position, and set up the initial position, which is not to equilibrium, and P0 0. So the way that it doesn't move anywhere, and modify only the X bar parameter and see what happens. And I will do several 5 to 10 attempts, and the maybe an impression, but I want to just open it to in the analogy to the in the analogy to the free space, we are just asking the question whether the uncertainty of the quantum particle will be kept or changed. And if changed, will it grow or decrease? So it is one aspect of the problem. Another one, mathematically, through the class, we did prove that the lowest possible state is
0, 1.
No, the number of state is 0. Okay, the energy will be above 0. It will be it will depend on the curvature, and the shape of the function will be Gaussian with certain width. So now, what is the definition of the eigenstate?
Was it
Roughly, not for the
n plus 1?
Forget everything we did last 2 weeks or even month. Just from the beginning, what is the eigenstate?
The natural energy levels.
Okay, and in sense of the wave function, what is the eigenstate? Like, what is the eigenfunction?
Peaks.
Huh?
Peaks.
Yes, but what is mathematically? Like, I do not need to go to college to show some peaks. Like, what is certain about this peaks? Why there amount of functions with peaks that would satisfy the eigenstate equation is much smaller than random number. Like if you write a sine or cosine function, it also will have peak. But why just cosine function is not an eigenstate of the Hamiltonian for harmonic oscillator? And it is, let's be not like mathematical, but not very rigorous. Like how do you interpret? What does it mean eigenstate? Do we speak about eigenstates in when we solve time dependent Schrödinger equation?
Yeah.
What would happen if you start from the eigenstate? How would it change in time?
Would it move, right?
Exactly. Yes. So eigenstate, it means. Do you remember some? Do you have some memories about postulates of quantum mechanics?
Yes. Yeah.
So, how long would the state, would the system exist in the quantum state if the state is eigenstate?
Forever.
Huh?
Forever?
Yes.
Right? Yeah.
What does it mean it stays forever in the state?
It'll stay there while something at the time.
And
Because it's a natural value, well, energy value.
right. So the state, the function, the function will not change in time. Even if we apply all bells and whistles for dynamics, it will show no dynamics, right? So it is one of the ways to, I'm going to say something very silly, but correct. So suppose we are hired as a team to solve, to find eigenstates for some equation, for quantum one-dimensional problem, and we do not like advanced math. How can we do it? Like silliest way, silliest but correct way. Draw a random function, plug it into our code, and see if it will change with time. If it will change with time, it is not an eigenstate. If it will stay unchanged, then it is an eigenstate. Does it make sense?
Yeah.
Okay, so now let's make connection to the stuff on the board. Let's prove that Gaussian with one and only one certain width that is determined by curvature of the parabola, by frequency and mass, will be an eigenstate, will not change over time. So it is an expected answer. If suppose, not suppose, we will do it. Suppose I am running this initial Gaussian state with different parameters of x bar. For all values except the very specific one, it will show some dynamics. And you will see which dynamics. Maybe if you're running, you already see it. But for one specific one, that will be literally equals to like 2h bar over m omega. The shape of the wave packet will not change in time. It will stay the same. So we are going, in some sense, numerically prove that Gaussian wave function with certain widths is an eigenstate of the harmonic oscillator Hamiltonian. Make sense? So, and now we will do why I called myself silly generator of silly ideas, because we do not need to do it if we have mathematical tools or if we have computers that can find eigenstates. But suppose we are poor in math and poor in computers. Then we can just make spawn different, screen different values of the width parameter, do a fair job of recording what comes out, which dynamics come out of it, and select the value which gives minimal dynamics or no dynamics. Make sense? Okay, so I'm going to do the same, and you can do it independently or follow me. So you can either take the same code you were using for previous two labs, or the one that I just sent, which is the same with a couple of lines changed. You can change these lines yourself or follow this made up help. And before we move forward, I would like to just check this Spencer and Connor if there are any questions to this general element statement. No? Okay, thank you. Thank you for that. Thank you, Spencer. I can just clear out of this one of my favorite tools. So it proves that the speed of light and speed of electrons is fine. It takes some delay. Okay, I'm going to share the screen a little bit. Here is the code that I did send, and the x var variable in the line 30. Just before I start running it like crazy, I would like to check where I do define the potential. So you do, if the variable is defined several times, only the latest one matters because it overrides stuff. So 3.35 or 34 is important. And the equilibrium position is 100 atomic units. The parameter of mass times frequency times divided by Planck constant is set up here. So I will interpret it as mass times frequency divided by T. And intuitively, I expect that one divided by this parameter would be correct answer. But let's check. Maybe I'm wrong on something. Maybe there is a error accumulation. So this line 34 I determined later. And now I'm going to check at the beginning of the course that the code. So P naught is 0. Okay. This H bar and mass are equal 1 because we are in atomic units. So we are at the same point in the center of the parabola. And then dx is 0.4. And I'm just I want to double check for the number of points. PPS 500. So if PPS is 500, dx is 0.4. It means the overall simulation box is 200, right? 5 times 4. Okay. So I will be changing only the stuff and maybe plotting. Okay. This stuff in the center. And first surprise. So not surprise. First it expands, right? As we were expecting. So you see that it contracts better. So it's quite different from the free particle without force. Right? So it is one of the answers that are questioned in the set of assignments. Like, what is the motion that width performs? It does perform oscillations, right? And in some sense, we do need to speak. If we describe oscillations, we can describe them by 3 parameters: frequency, phase, and amplitude. Phase is not so important here.
So how would you find the length of that? Is it just
Let's look through the code. It was, I believe it was the assignment of Kennedy to explain to all of us how to extract a variable and say it. So it is already present in this images, but let's look once again into the code. So the place of the code inside the loop. So here starts, here ends. And here it processes the different variables for the expectation value. I'm going to get back to PowerPoint and just prove that this line one. Yeah, value answers 3. I like this very well. So let me just remind to all of us a little thing that I just do not know how to ask appropriate questions, but I'm sure you know this answer because it is a principle of setting grades in the freshman courses. So if there is a function, what is the center of the distribution? It's distribution times position times dx, right? You don't need explanation. Now, if I will redo this equation in the following way, I will do x minus expectation value of x. What will be the answer?
X.
It's not for the grade, but
The middle between X and expectation value.
Delta X.
so if this operation gives expectation value, it is a number.
0.
Super, exactly. Correct.
Holy cow, I thought you put it inside of the function f of x. My bad.
No, not inside the function, multiply.
Very good.
But original idea was to see how much the in freshman courses x is great, right? How much the grade differs from the average. But if we take linear the things to the left and to the right from the average, they decline each other. Right? But if we practice the square, then we do not have negative values. We do x minus x squared dx. Then this stuff will be width parameter. Right? So if f of x is wave function xt, or better wave function absolute value squared, right? Then we just practice this equation and call it that it will be our main variable. So I'm going back to the code and look here 146. Value answers by so prop 3 is absolute value squared. It's defined somewhere before. And then the AVG3 is expectation value that we were just drawing. Okay? And this summation of x minus average squared as for the distribution is exactly literally the way how we program, how we define the width of the distribution. Make sense? And since there is a thing that was really nicely explained by Kennedy. So anytime it comes through the loop, the value of this variable is being overridden. So we need to store it. And this thing, variance 3, is accumulating the value. So I want to open uh, figure, and type here what is 3. So it oscillates between 4 and 32, and definitely it is not. It is not. High state because it changes over time. So what else we can see in this image? Whether I will start thinking of my homework assignment. So I'm doing full screen. Maybe there's a better way to that. Also doing phone. So see. Now with phone. Paste.
If you want an easy way to
Yes,
insert
yes, I do.
that, if you go to insert, you can go to the screenshot, and you can pick one of your windows to just put into the PowerPoint.
Start screenshot.
Yep, and click on that. And then you have all your different windows, so you can go and just click on your figure 6.
Whoa, super. I was lying. The homework can be done in 5 minutes, not in 10. Most of the time, I was assessing is just for copy pasting images. Thank you, Jared. It's really cool. So, someone is giving a comment, chat. Wow, that's actually really useful. So, when the power given to me by Connor, I give +1 extra credit to Charles. So Connor is enthusiastically.
Or if you don't want the whole window, you can go to screen flipping, and then you can select how much of it you want to. But that requires more work.
Okay, so where do I?
Back to insert screenshot,
Okay.
and then click the screen flipping at the bottom. So now then you would select the part of the graph if you don't want the whole deal.
Yeah, super.
Just a couple different ways.
That's cool. That's really cool. I like it. And I just want to add the comment because, like, if I need to do this assignment myself, I tell that it is x bar equals 4, and observation is it's huge oscillation. Huge oscillation between 4 and about 50. So it starts at 4. What was our original value, right?
Yep.
You set up x y equals 4, and it starts here, and then it starts drawing. So one way. So let me think. What do I want for my happiness if I am the wave packet?
Probably in the middle.
Super. Yeah, we are on the same page. In the middle. If I can expect that if I make initial x bar equals 32, it will start contracting. And if I take a point somewhere in the middle, it should stabilize here. It's only a hypothesis, but we can prove it. So midpoint between 4 and 32.
16.
Yeah, 16. Let's do maybe 18.
Yeah, 16.
change the middle, 0 and 32.
Okay.
Yeah, so
Okay. So I'm going back to, and I need to go to the line 30. So I'm putting here like 18. If I'm really picky and I fear to make errors, I can rename the code. It's 18, and I can rename the packet x1 18. So if I expect that there will be big science behind it, then it will create another. Okay. I do not know if I will need all this stuff because if you close my screen, I probably will just close all these windows. If there are 6 windows generated at each run, then 10 runs will make it like 60. So, okay. So you see, it is in the middle near the target, and it became wider than it was before, right?
the
18.
18 off each side.
Yeah, well, it will be 18 if you measure here, but standard way is to measure in the middle.
Okay.
And if you read experimental data with like spectral line widths, or if you analyze like statistical grades or whatever, they use FWH, some abbreviation, which means like bits at half of the height. Okay, so it still changes, maybe a little bit less. And now, at the beginning, instead of getting wider, it starts getting narrower. So it means like we overshoot it by trying to pick the target.
So we're trying to make it not.
Exactly. And record our observations and make big science out of it. Like comment that we are on the way to find ideal eigenstate without taking analytical mathematical derivations. So I'm repeating the same thing to figure for variances. And now from 18, it goes down to like 7. We are not yet at the point, but the amplitude of the oscillations is small, right? 32 minus 4 was 28. Now 18 minus 7 will be like 11. So we are on the right way. We can make the next shot maybe like 13 and see what happens. And the whatever word Joe. Screenshot. Yes. So cool. That's good. And account X bar was set up to 18 Philippines, and every it shrinks. Then let's see. until U is smaller than before. So next step will be to take like 13. So the method close all this windows. So, so we're going to try 13. I'll say this text one. Now, by human eye, it looks a little thinner. And it still becomes narrower, but for my human eye, it looks a little milder. So it looks like we are on the right way.
Ours takes a lot longer than yours.
Okay. So which value is
13, and then it goes down to about 9.7.
Uh-huh. Yeah, 9.7. So what would be my next?
11.5.
Okay, yeah, let's
Or
try.
11.
Let's try 11 before. And I want to record the image just in case if I need to screen. And I want to train this new skill. Screen. Come if it was for 13. Decrease.
At 111.5.
13
So,
more. Next row. 0.4 and 10. No. It's very close to solution. As human, I don't see much difference. But when we will look on the observable, I bet there still will be oscillations and we can keep minimizing. And depending on what it does at the beginning, we can increase or decrease. Like if the width this time, if at the beginning it grows, then we need to increase it. If it decreases, we need to decrease it. So it's kind of pilot direction. Whew. 45 minutes, I can't believe. I think it should be doable in 5 to 10 minutes. So so now it oscillates from 11.5 to 10.75. So amplitude of oscillations is like less than 1, but it still oscillates. And for human eyes, it's already hard to see, but for observables show noticeable oscillation. So I would try 11.15. I see a little mismatch between method 2 and method 3. So this orange and red line slightly differ from each other, but it is almost unnoticeable. There is another thing that is not needed for the homework report, but if one would look at the expectation value of position, which will, even if we start at the right point, it may oscillate slightly. So if we look on the expectation value of position and oscillations of the width, we'll see that they differ by factor 2. So the width oscillates twice as quicker. And there is an intuitive explanation, which one can see if one sets the initial position non-zero, if it truly oscillates. So when the wave packet bumps into the wall, it contracts. When it bumps into the opposite wall, it contracts again. In the middle, it expands. So in one full rotation, it contracts and expands twice. Now it goes up. If I really want to find it really precise, my next try will be 11.17. Yeah, it looks like very close to what we need. And it shows that the shape of the function is almost the same as we were discussing at the beginning. So if the shape is not changing, it means it is a true eigenstable. And we found it just by screening different widths without solving math. Suppose that I do I take differential equations, and I just try different functions until I see that they do not change in time. And there is a qualitative difference between um, particle in the free space and particle in the oscillator. So in the free space, it just expands or contracts if you fluid at the time. And in the oscillator, it oscillates. Okay. So right now we do see oscillations, but the difference is in the fourth digit after the period, falling for 6 digit. Because for multiplications it is precise answer. Okay, so the next thing is just to document this effort. Let me check this Spencer and Kohler if this information here is sufficient for the completion of this homework or any other questions so far. Okay, so I do not have any other things. Okay, thank you, Specimen. Thank you for that. So I do not have any other things in the program. I can just sit here and answer if any questions pop up. But the although we close to successful completion of this homework and we have time, but I do not want to overload your and my brain with other things. Let's just accumulate energy. We'll continue discussing research projects on Friday. I will split the lecture between you two and portion of the lecture will be about selection of the research projects. Okay, thanks again. You're welcome to either stay or leave, but there is nothing additional scheduled to what we will be doing. So